Hi everyone, welcome back to the Heterogeneous Parallel Programming class. We are at lecture 7.5. We are going to introduce OpenACC programming. The objective of this lecture is for you to understand how to write an OpenACC program. OpenACC is a new industry standard, and it was originally proposed by Portland Group, which is part of NVIDIA today. And in this kind of programming paradigm, which is similar to OpenMP, where we actually have a compiler to do a lot more of the work that you have been doing with CUDA or OpenCL. So in this lecture, we're going to introduce the basic concepts and pragma types. And you will be writing compiler directives called pragmas to instruct the compiler to do the detailed code generation for you. And then we're going to use some simple examples to introduce the concepts. There's a little bit more background information. And the OpenACC programming interface consists of mainly three parts. The first one is compiler directives, or pragmas. And the second one is a set of library routines. And the third one is environmental variables. And these all together can be used to write data parallel Fortran, C, and C++ programs that run on accelerated devices such as GPUs and CPUs. So the heart of the programming is about inserting OpenACC pragmas into your program. So in C and C++, we actually have a long-standing use of hash sign pragma directives to introduce or provide compiler with the information that is not specified in the standard language. So if for experienced C programmers, we know that we can use the pragmas for various things, hints to the compiler. And OpenACC builds on this mechanism and provides a special set of pragmas that the compiler can use to generate parallel programs for execution on accelerators. So all these pragmas are going to start with hash sign pragma and then ACC. So keep in mind that there are many other pragmas that are in use in the C programming environments. So when you start with pragma ACC, that means that these pragmas are meant for an OpenACC compiler. So here we show a very simple matrix mixture multiplication code in OpenACC. And we show that the function is just like the host code, where we have a function that receives parameters, pointers to the output matrix, the input two matrices, and the height and width of each of the input and output matrices. And the input matrix is a m height by m w, and then the n matrix must be of the same. The height of the n matrix must be the same as the width of the n matrix. So that's why we can just use m w as the height of the n matrix. So we don't need to specify n height. And the output is going to be just the height of m and the width of n, so we don't need to specify the output dimensions as well. And here we show that the code has essentially the same structure as the sequential code that we introduced in the matrix multiplication lecture. So we have two levels of loops, I and j, that will go through all the output matrix elements. And then for each output matrix element, we have an inner product in loop that will produce the dot product or inner product of one row of m and one column of n to produce one element of p. So this is really just the sequential loop that we will be writing. And now, in order to use OpenACC, we can just insert two pragmas here. The first pragma says the following loop is going to be a parallel loop. So this is parallel loop pragma. And in order to execute this loop in the accelerator, we need to copy in the input matrices m and n. And then after the execution, we need to copy out the output matrix P back into the host. So the concept of ACC is extremely easy to understand once you understand CUDA programming. And so here, we're really just instructing the compiler to generate the device memory allocation and data copying sequences for us. So in order to properly allocate memory and copy data, we need to tell the compiler the size of the data structure being copied. So the copying pragma statement has a size of m, and it tells it linearize the M matrix into a one-dimensional matrix with elements from 0 to mh times mw. So essentially, we're talking about a linearized view of the two-dimensional matrix M with m, h times mw elements. And then we do the same thing for n. And so we are using mw as the height of n. So we have the same statement here. And then for the copy out, we have p, and p is just the height with this of m and the width of n. So this pragma allows us to tell the compiler that the next for loop should be, or just the next loop should be parallelized. And we need to copy in all this state, both m and n, and copy out p before and after the execution. So here we see a second pragma, and this pragma says the following loop should be executed in parallel. And because we have already covered the data copy in the outer loop, we don't need to repeat that in the inner loop. The data should be already on the device. So this is the reason why I mentioned that once you understand the CUDA programming interface, it's very easy to read OpenACC and understand what we're instructing the compiler to do on our behalf. And the compiler will actually do the detailed code generation equivalent to what we're doing when we write the CUDA code by hand. So just some quick summary. The code is almost identical to the sequential version, except for the 2 lines with hash pragma at lines 5 and 3 and 5. So the OpenACC uses compiler directive mechanism to extend the base language, which is C in this case. And the pragma at line 3 tells the compiler to generate code for the I loop at lines 4 through 15, so that the loop iterations are executed at the first level of parallelism of the accelerator. And the first level of parallelism actually pretty much correspond to the thread blocks. And so these outer loops are going to be executed as different thread iterations of that I loop will be executed as thread blocks in the GPUs. And then the copy in clause and the copy out clause specify how the matrix data should be transferred from host to device and from device to host. And then finally, the pragma at line 5 instruct the compiler to map the inner J loop to the second level of parallelism on the accelerator. In this case, it's mapping the J loop into the threads. Each iteration of the J loop will correspond to a thread in the CUDA programming environment. So the main motivation for OpenACC is that OpenACC programmers can often start by writing a sequential version, and oftentimes they already have a sequential version of the code. So then they can just annotate their sequential program with OpenACC directives and leave most of the details of writing the code to allocate device memory, transfer data to device memory, and launch kernel and so on to the compiler. So this reduces a lot of the tedious work involved in writing parallel code. But so OpenACC code can also be compiled by ignoring the by ignoring the pragmas if we need to use a non-OpenACC compiler. So if we, in the CUDA situation, when we write a piece of CUDA code, we have to compile that code with a CUDA compiler. But here, we can simply use another compiler such as GCC to compile your OpenACC code, and that compiler will function, should be able to function pretty much correctly for most of the programs by ignoring the pragmas, because these pragmas are just hints to the compiler. However, many OpenACC programmers also experience some issues that some OpenACC pragmas are hints to the OpenACC compiler. So these hints may or may not be the compiler may or may not be able to act exactly as what we're trying or envision the compiler should be doing with those hints. So whenever the compiler fails to follow these hints, then the performance of the OpenACC program can vary dramatically. In fact, in some cases, the compiler may just generate a sequential code, and then the performance can be much, much less than what we expected. And when these situations happen, it may be hard to figure out why the compiler cannot act according to your hints. So this kind of situation happen much, much less so in CUDA and OpenCL programs, because as a programmer, you're doing all the work. So you have much, much more control over exactly what's happening at runtime. But since OpenACC goes through the compiler and have the compiler do a lot of the code generation work, and whenever something fails in that process, oftentimes it can be very hard for a programmer to figure out why the compiler failed to deliver that performance. So now we're ready to begin to talk about the specifics of how we can use OpenACC, and it will be useful to first understand the terminologies and what the OpenACC literature used to describe the hardware. So the OpenACC device is described as multiple of these execution units. So these execution units are essentially mapped to streaming multiprocessors for the execution in a CUDA GPU, and then each execution unit will have all these threads, and so these threads are actually equivalent to the CUDA threads in the CUDA threads in the execution, the CUDA model. And then what is a little bit different from CUDA is that every thread can also have vectors in that thread. So in many ways, these vectors are somewhat similar to the warps in the CUDA, but these vectors are usually correspond to the CPUs, where we have these multiple. We have the SIMD instructions in these CPUs. So oftentimes when we implement an OpenACC programming model on a particular hardware, even though there are 3 levels of hardware parallelism, oftentimes only 2 of them are really used in a particular piece of hardware. And currently, OpenACC does not allow synchronization across threads. So unlike CUDA, where whenever the threads belong in the same execution streaming multiprocessor, these threads can synchronize with each other with various synchronization. Currently, OpenACC does not allow the programmer to specify such synchronization across threads in the same execution unit. And this may actually change in the future. So here we show the OpenACC execution model. This is how the programmers describe the parallel execution behavior of loops. So whenever we have a sequential execution that reaches a particular piece of code that can be executed in parallel, we can launch parallel execution by requesting the generation of GANs. And these GANs are really the equivalent of thread blocks in CUDA. And so each GAN will have multiple of these workers. and these workers will correspond to the threads in CUDA. So all the threads will execute, and then at some point they may converge, they may further span out. But after the parallel execution, they will come back and synchronize. If we do a synchronization instruction in OpenACC, then the host will wait for the device to finish this execution and converge back into sequential execution back on the host. So all the data copy in and out will happen before and after the execution. So this also corresponds to the OpenCL work group and work items. So once you understand CUDA and OpenCL, it's fairly easy to understand what you're really telling the compiler to do in your OpenACC code. So now we have completed the basic introduction of the OpenACC programming model. For those of you who would like to learn more about OpenACC, I'd like to encourage you to read the specification of OpenACC online, and also you can read Chapter 15, which is an introduction to the OpenACC programming model. Thank you.